space is certainly not empty. It's full of these lovely little carbon footballs dancing through the gas clouds.
The new James Webb Space Telescope detects molecules between the stars in dramatically enhanced detail. It's creating scientific excitement. The European Union has funded a large project called NanoSpace. It's bringing scientists together to study them.
It's a great project because there's a community spirit. We all want to work together. It's enormously gratifying to see that there's all this excitement and all this fun about discovery again, about fullerenes, nanotubes, aliphatic materials, other sorts of molecules.
So we've managed to bring together quite different communities. We have the astronomers, we have the astrochemists, laboratory scientists, theoreticians, and they're all coming together at a very, very exciting time. There is the new James Webb Space Telescope that's going to produce enormous amounts of very detailed data that will tell us a lot more about where these molecules are. And we are getting revolutionary advances in theoretical treatments that we can use to understand.
So that is the idea of NanoSpace, to join very different disciplines to learn how to speak each other.
Basically, I'm doing Raman spectroscopy to characterize carbons. So I'm very excited to be here because I want to find opportunities to work with people and to help by characterizing their samples.
In this field, to make progress, you need to understand what's actually going on. And so, for instance, a small detail in our models for the charge state of fullerenes, one of the key parameters that we need is something like, for instance, an electron attachment rate. Now, we're astronomers, we're not going to be able to determine that electron attachment rate. You need very high-level, sophisticated experiments to actually measure that.
I have a personal wish because, yes, I've been working on a particular problem which is related to infrared emissions that is observed everywhere in space, and I'm trying to build something to measure that in the lab, which is really a big challenge. And in fact, regarding all the new data that will come out and what we can do in the lab, I think that by going to more slight extension from near-infrared to mid-infrared, I really hope that in the lab I will succeed to measure things that will be comparable to what will be observed very soon.
In order to identify any species, any complex species in space, we need a perfect spectroscopic match between the observations and the theoretical and laboratory data. For that, you clearly need an interdisciplinary approach. You can only do that, by networking.
I think what I would personally really like to learn, and hopefully the cost action can give us the answer to that, is really how the fullerenes are being formed in space, and really look for evidence for related molecules. At the moment, we know that there's carbon-60, there's carbon-70, but how many other species related to the fullerenes? There must be others.
The fullerene molecules are made of carbon atoms. The atoms act like girders, connected together, for example, to build a carbon-60 sphere, or a million other structures. These fullerene structures are found throughout space, but how and where they're being created is unknown. One idea is that they form from the outflows of dying stars, and after that, as they travel for millennia through interstellar space, encounters with particles and radiation change them. In space, there's lots of time. Time for an unfamiliar chemistry to be going on.
It may be important for making more complicated structures out of simple molecules. The easy way to understand that is to assume that an energetic particle, proton or electron, cuts off hydrogen, and then we have a reactive dangling bond. Then molecules with dangling bonds can join together and make a more complicated structure. This can also happen without irradiation, but it may take a bit longer, let's say a couple of million of years.
Probably, interstellar space is a vast reservoir of organic materials that we won't have seen before. Some of these compounds could be relevant to the origin of life, but we haven't uncovered them yet.
Of course, it would be great if at some point we start to calibrate our instruments. Somebody from this action could actually provide us with dust to do that with.
When the project will finish, I dream that we'll be able to say, if we see the spectra, we can clearly identify which kind of molecules are formed, and, for example, how these molecules has been transferred to the Earth and can start to formation of a life on our planet.
Yeah, I hope we make a success to find abundant carbon in space.
We don't know how they're being formed. We don't know yet how they're influencing the chemistry in space. And that's, of course, one of the things we want to try and answer in the course of this action.
I think that already would be great. But I think there's enough people in the consortium to make sure that we'll go way beyond that.